Okay, so this is part two of the applications problems. And so now we have rotations and revolutions on there, something you need to know, but we could use it interchangeably on there. Rotations is a good example of something that's rotating is like the earth spinning. So one day, so it's spinning around itself. Revolutions is spinning around something like the earth spinning around the sun or rotating around the sun. And it takes 1 year. So that's the difference between rotations and revolutions. So in 115, we have planets on Earth rotates every 24 hours, actually 23:56 minutes and 4 seconds, and has a diameter of 79.26. So all the stuff that we're talking about, we want to know if you're standing at the equator, how fast are you traveling? So we're talking about the linear speed, and then computing with it the linear speed at 24 hours and then computing it at 23 and 56 seconds. And I mean, sorry, 56 minutes, 4 seconds. So that's what we are actually calculating right now. So we're going to do first the calculation of 24 hours. The main thing that we need to know on this one here that we already have is that we have 24 hours is one rotation or 23 and 56 seconds is one rotation. But we know that the radius, because we're going to be using, because it's per rate on there, we're going to be using V is equal to omega R. And so the radius we still need to know. So the radius here is going to be 3,163 miles because we're given that 7,926. So if we're going to talk about the the linear speed, because that's what we're asking here, we have the radius here. What we know is that when we have this, it's going to be v. The angle that's being made, omega, is that we have that it's going to be. And we could calculate it over here, that omega is going to be one rotation in 24 hours. That's the rate at which the omega is going to be. We're going to change that, and that's going to be one rotation, and then it's going to be 2 pi radians. And so the rotations are going to cancel, and you are going to be left with 2 pi radians over 24 hours. Now, you guys probably already figured that out, that one rotation around the sun is equivalent to 2 pi in 24 hours. So we're going to use that. That's actually what we just found is our omega. Rotations canceled, change to radians automatically becomes our omega. So that's going to be 2 pi radians over 24 hours is our omega that we're filling in right there. And then we know the radius is going to be 3,963 miles. So when we're going to this, anytime we're calculating, the radians automatically go away, and the linear velocity is that we just calculated, and it turns out to be about 1,038 miles in 1 hour, so per hour. So that's what would have calculated on there. And so so when we are calculating that, that's what we get in 24 hours. We now need to calculate it in 23 hours, 56 minutes and 4 seconds. So in order to calculate that, we need to now do the same thing that we're going to do. And so we are going to calculate the 56 minutes. And because we already have the 23 an hour, so we need to change the minutes into hours. So we have 1 hour, 60 minutes. So that's going to cancel the minutes, and it's going to be approximately 0.9333, almost 1 full hour, which makes sense because it's 56 minutes. And then we have 4 seconds that we need to change to hours. So that one's going to be 60 seconds is going to be 1 minute, and then 60 minutes is going to be 1 hour. And so the minutes cancel, seconds cancel, and we are approximately 0.001111 hours. So 4 seconds is that many hours, 56 minutes is that many hours. So when we calculate the linear velocity of this one here, we're doing the exact same thing, but now what we're going to do is we're going to do that the angle, once we add these up, is going to be, instead of 24 hours, it's going to actually be the radians of 2 pi over 23.93444 hours, which just means that I'm taking the 23 hours, adding the 0.93 parts of that hour plus the seconds, that part of the hour, and it gets almost 24 hours on there, but it's the same thing. It does one revolution in 23 hours, not really 24 hours, and hence that's why we have a leap year every year, because we're really not having the full 24 hours. And so then when we multiply this, the radius is still the same. So it's going to be 63 miles. And so when we calculate, the radians goes away. And so your linear velocity is going to be approximately 1040 miles per hour. So if we are to write a sentence, we are going to say the Earth is spinning approximately 1038 miles per hour if using 24 hours, and 1040 miles per hour if using 23 hours. Okay. And so that is your answer right there. Very good. And then the carousel, a boy wants to jump onto the playground carousel, and it is spinning at a rate of 30 revolutions per minute. So the 30 revolutions per minute is important because that's revolutions. And we have this to be that we want to find the how fast does the boy run on there? So how fast is that boy running? That's going to be our linear speed, which is v, and then we want to find omega there. And so this is the diameter of it. So that's going to give us the radius is 3 feet. And so to find omega, we're doing 30 revolutions per 1 minute. So we need to change that to an angle in radians. So it's going to be 1 revolution is 2 pi radians. And so that is going to calculate that. And we end up that it's going to be 60 pi radians per 1 minute. And so that's the angle that's being made because it's in radians. We want to know how fast the boy is going. So we want to know what V is. And we already have that this is going to 60 pi. That's the angle in 1 minute times the 3 feet, which is your radius. And so we end up, and that's minutes. And we want to have this, and that's what you would get on there, but we want to go to the nearest foot per second. So we need to change that minutes on there. And we're going to change the minutes by putting in 1 minute in the numerator and 60 seconds in the denominator. That's going to cancel. And so our linear velocity is going to be 9.4247 feet per second. So the boy should run approximately 9 feet per second. Okay. And then this one here is with the music. Okay, let's erase this. on here. So some people still play with phonographs collection. Okay, so we have a turntable and it is spinning at 12 inches diameter, rotating for 33. So here we have revolutions per minute. So again, revolutions on there, that is your angle, omega. Well, at least we could get it from it because we're going to change the revolutions to radians per hour. What is the angular speed, which is what we're trying to find. So this problem is not bad. It's not talking about linear velocity. We do have that the diameter is a 12-inch, so we have the radius is going to be 6 inches, but that really is just extra information because all we want is omega. And so I know that this here is going to be um, revolutions in 1 minute. So that means that I need to change the revolutions. One revolution is 2 pi radians. So all I need to do is get it into radians. That's going to cancel. And when we get this, we're going to get 2.0943. This is the angle that's being made at 209 radians every minute. So the angular speed is approximately 209 radians per minute. And that's what we get there. And then here's the NASA, and one is going to be in red. So this arm is in red, and then this arm is in blue. And it all is just doing is that it's spinning this arm. It just spins round and round and round and round and round. And so we have that it's going to be 200 miles per hour. That there is giving us our linear velocity, right? So that's the miles per hour. Distance over time is linear velocity. So that's going to be 200 miles in 1 hour. And then how fast is the wheel rotating? So we want to know what angle is actually being made. So we're looking for the rotations in there and how fast it's actually rotating. And so we are given some information in this here. And so over here, we're telling us that the diameter of the arm is 58, so the radius is going to be 29 feet. So here we have 200 miles per hour. I have a radius that's in feet, so yep, dimensional analysis, we have to convert it. So we need to convert the 200 miles per hour into feet per hour. So we know that this is going to do 50 to 80 feet, and it's going to be in 1 mile. And so that's going to cancel. And so the 200 is going to be 1,056,000 feet per hour. So we're going to have that to be feet per hour. So that means that the linear speed is going 1 million feet per hour. So now how are we going to use that? Well, that's the linear speed that we're going to get there. And I want to know, I know that I need to get to omega somehow. So I'm going to do the 56 feet in 1 hour. That's our V, and then that's going to go on there, and we're going to be able to do omega, and it's going to be the radius, and the radius is 29 feet. So when we calculate this, we're going to get that omega because we're going to divide this. So we're going to multiply this by 1 over 29 feet over 1. That's going to cancel, and I need to do the same thing on this side. 29 feet, the feet are going to cancel, and so we're going to get the omega. So it's going to be 3, 6, 4, I'm sorry, I did the comma in the wrong place. 36,413.79 radians per hour. And so that's what we have the angle to be. So the only problem there is that's the angle being made. They want to know how fast it's rotating. So the rotating is one rotation is 2 pi. So we're going to change this to rotations by multiplying this radians in the denominator, revolutions or rotations. Since this is rotations, it's going to be the same thing. So it's going to be 2 pi because this is radians, and then this is going to be 1 rotation. So that's going to cancel. And so the answer here, what we're going to get is about 5,975,435 rotations per hour. So it's rotating around almost 6,000 times. It's going around and around and around. So the answer here is the centrifuge is rotating approximately 5,795 rotations per hour. And there you go. So make sure you review these.